Hello guys, let's have a look at the question. The question is as follows. A rocket is stationary on the launch pad. At time t equal to 0, the rocket engines are switched on and the exhaust gases are ejected from the nozzles of the engine. The rocket accelerates upwards. Figure 1.1 shows the acceleration of the rocket as it varies from time t equal to 0 to time t is equal to t subscript f. Now here we notice that there is a certain amount of time or a certain duration of time for which the rocket has a constantly increasing acceleration, and there is also a duration of time where the rocket has a constant acceleration. As to the logic which allows the rocket to accelerate upwards, it is the logic of conservation of momentum. As the rocket expels gases to the left, let's assume, or downwards, the rocket is forced to move upwards. This is in accordance with the law of conservation of momentum. Let's take a look at the first question. The first question says, define acceleration. Acceleration is defined as the rate of change of velocity of a body. The rate of change of velocity of a body. Looking by this logic, we know that if a body has an initial velocity u, which changes to a final velocity v, then the formula for acceleration a is v minus u divided by the time interval or the time instant t. Moving on to part B of the question. On figure 1.2, sketch a graph to show how the speed of the rocket varies between time t equal to 0 and t equal to tf. Now, going by the logic, there is a certain duration or a certain interval. Let's call it t1. From this time interval, t equal to 0 to 2 equal to t1, there is a constantly increasing acceleration, which means the speed or the velocity of the object will be increasing at an exponential rate, which is why we show the same through a curved graph. This is for the time instant t1. From time instant t1 to tf, we notice that the body has a constant acceleration, which translates to a constant slope of a straight line on the speed versus time graph, which is why we denote the same as a straight line. This is how the graph of speed versus time varies for the exact acceleration versus time graph. Moving on to the next part. Sometime later, the rocket is far from the Earth. The effect of Earth's gravity on the motion of the rocket is insignificant. As the rocket accelerates, its momentum increases. State the principle of conservation of momentum. The principle of conservation of momentum is as follows. The conservation of momentum says exactly this. It says the total momentum of a system of bodies before collision is exactly equal to the total momentum of the system of bodies after collision provided, and this is a very important condition, provided there is no external force acting on the body or the system of bodies. We understand that there is no external force acting because of this statement which says the effect of Earth's gravity on the motion of the rocket is insignificant. This is an indication that there are no external forces interfering with our system of bodies, which further strengthens the conservation of momentum. Moving on to part 2, explain how the principle of conservation of momentum applies to the accelerating rocket and the exhaust gases. To explain the same, let's take an example of a rocket executing said motion. Here we have a rocket which propels itself outward or upward by expelling gases downward. Let's assume that the mass of the rocket is m, while the mass of the gases is m. Let's assume that the gases are expelled with a velocity v downward. The rocket is, let's assume vg. Let's assume that the rocket is expelled upward with a velocity vr. Now, we understand that before the gases are expelled, the rocket is in a state of rest. So are the gases. So total momentum before collision is equal to 0. While after collision, we assume an upward velocity as positive, a downward as negative. So the momentum of the rocket, momentum is given by the equation P is equivalent to mv. So the momentum of the rocket becomes capital M into plus Vr plus mass of the gases into minus Vg. The reason I'm writing a minus sign is because velocity is a vector and velocity follows the following hypothesis. A velocity vector directed upwards is positive, while one directed downwards is negative. Rewriting this equation, we get velocity of the rocket Vr is equal to m into Vg divided by capital M. So this is the law of conservation of momentum applied to an example scenario of rocket propulsion. The reason I am able to apply this scenario is because the condition of no external forces acting is obeyed because Earth's gravity is said to be insignificant, and the body is considered, or the system of bodies are considered to be obeying because the equation is validated here. This is a numerical example of how the conservation of momentum is applied and verified for an accelerating rocket and the exhaust gases.